Our project is test suites as a source of training data for static analysis classifiers. We developed a novel method that uses test suites to automatically generate labeled data for static analysis classifiers. We then implemented the method in a software system, and in a case study, we generated a large quantity of labeled data for many CWE, or common weakness enumeration of miters, using the Juliet C++ version 1.2 test suite. With that, we created 4 types of classifiers and tested them on holdout data. Also, we tested something called speculative mapping that I'll speak to in detail later in the presentation. And we devised an effort-efficient, partly automated method to map static analysis tools to test suite taxonomies. In future slides, I will speak through the details on the design on the right. So, our project uses classifiers for static analysis. The problem it addresses is that static analysis tools output too many warnings or alerts, and classifiers help us to automate much of the handling of those warnings. So looking at the figure on the top left, today, as a normal part of testing, static analysis tools are run, one or more static analysis tools are run on code bases, and each of them outputs a set of alerts. Alerts that share the same line, file path, and code flaw condition, like CWE 190 or int31-C, map to the same meta alert. A meta alert is a construct that we use to more efficiently adjudicate the meta alerts. Adjudicate means have a human manually determine if they're a true positive or a false positive. It's also more efficient for us to aggregate that information into a meta alert to do machine learning classifier predictions. So today, for the most part, static analysis is manually examined and adjudicated, leading to the scenario you see at the top right of this slide, where with the blue bars, you can see a small number of the meta alerts have been adjudicated true and false positive, but the vast majority are in that red bar where they're indeterminate, or I. They haven't even been examined, and so there might be true code flaws that lead to severe vulnerabilities, but they were never examined, even though warned about. So the goal of using classifiers and of the project that led to this paper is classification algorithm development using automatically labeled and manually adjudicated data that precisely and with high recall classifies many meta alerts as expected true positive or expected false positive with a high confidence, and the rest as indeterminate. So there's this mixture of the auto-labeled and manual adjudication, leading to the scenario shown on the bottom right, where in this situation, half of the manual effort was cut into half because an equal number of meta alerts were predicted by the classifier to be expected true or false positive, with the same number of indeterminate meta alerts. Alternatively, there can be the same amount of manual effort spent adjudicating, and just more meta alerts can be adjudicated. So on slide 5, I highlight related work where the full references are in the paper. Delettra et al. Tested static analysis tool code flow coverage, and they found that coverage per tool averaged around 20%, Using multiple tools helps, but it compounds the too many alerts problem. Pugh et al. Did a large empirical study and found a mean time of 117 seconds per adjudication, analyzing an enormous amount of data from over 10,000 Google engineers' adjudications. In another paper, Data-Rich Google with Ruth et al. Developed classifier models that were excellent in accuracy at 85% at predicting false positives. They used really interesting features, including feedback from developers who were able to decide whether or not to fix code and in what priority after a meta alert had been determined to be a true positive. Cross-project classifier prediction is an area of research developed to address insufficient labeled data within a single code project. And our work is a type of cross-project prediction, but our focus is on quickly and cheaply generating new labeled data. Heckman and Williams' excellent and extensive survey of methods that classify and prioritize actionable alerts includes various features, types of active learning, and classification algorithms. They didn't, nowhere in their survey nor anywhere else, my team was able to find, were we able to find test suites being used the way that we have used them. NIST provides over 600,000 cost-free open source test suite programs in its SARD data set, and many non-NIST test suites exist as well, where test suites were originally developed to test coverage of static analysis tools and precision, and in my project, in the paper, we're using them to generate auto-labeled data. Machine learning with static analysis is pictured here, where in the paper we talk about how we use multiple static analysis tools. Although the system we developed can also work with a single one. We use a variety of features, some of which are provided by static analysis tools, others by code metrics tools, others by our own analysis, like of aggregated data from the other tools, and competing classification techniques. We compare lasso logistic regression, light GBM, random forest, HTO.ai type, and XGBoost. And we split labeled data into a training set and a test set, develop the model from the training set, and test it, validate it on the test set. So this slide shows some data about CERT audited archives that show typical issues for classifier data. There's this typical code flaw coverage issue. 10 years of adjudicated static analysis archives from work at CERT, my organization still lacks a lot of data. There's no data at all about many CERT coding rules. And for other rules, there's only all true or only all false. And that affects the classifier performance, not having the range of data. So the big inspiration that I had was, let's use test suites to generate labeled data. We want to rapidly, relatively cheaply generate that data, both for classifier creation and active learning. Let's see, I've covered the other parts of, there's one piece of data I haven't covered before. So in our project, we not only use the information about code flaws provided by the SARD Juliet test suite. But we also use CWE mappings to assert rule taxonomy for C, to transitively then generate labeled data for cert rules and for creating classifiers for those. So the system that we made for static analysis, labeling and classifier training is shown here. On the left, you see the data preparation side, where we input defect metadata from the test suite. We generate sets of alerts from each flaw-finding static analysis tool. We add mappings between checkers and conditions. Checkers are from the tool, conditions are from an external taxonomy like CWE. Some of those we gathered from the internet, some of those we generated ourselves. We generate source code metrics from tools like CCSM and Lizard. We also generated from proprietary tools as well, which, because of licensing, we're not allowed to mention their names. And we input source code structure metadata. Those go into a database, into a Mongo database. And then our scripts, we have many Python scripts. They generate ground truth alert labels that label them true or false positives. That label data is then split into 70% training data, 30% test data. And we create classifiers with the training data, apply it on the test data, and then compare the performance to the ground against the ground truth. Then we ran a case study using our system and Juliet CC++, which was developed from NSA CAS, and it contains 61,387 tests. We identified true positives automatically using the manifest file, an XML file in a SARD format that identifies precisely where a particular CWE is on what line and what exact file path. We identified false positives automatically by metadata embedded in Juliet's function name, whereby the string good is in the function name string, and that identifies there's no flaw present for a single CWE. Any other CWE we have no idea about. So here are our results after we used 8 static analysis tools on Juliet programs. You can see that we generated about 37,000 true positive labeled meta alerts and about 84,000 false positive labeled meta alerts. That's a lot of new labeled data. So that's a big savings in effort. A manual adjudication of any 121,000 or so meta alerts from non-test week programs would take an estimated about 3,900 hours at that 117 seconds per adjudication from that big Google study. However, any random 121,000 meta alerts are unlikely to cover the wide range of conditions and flaws covered by the Juliet test suite. And we want both true and false labels to better develop classifiers. So realistically, a much huger amount of manual effort would be required. So this is the kind of data we were looking for. Then we created classifiers and tested performance. The performance is shown here, where we tested on the holdout data. You can see for each of the 4 types of classifier, the types of metrics, accuracy, precision, recall, are good. We also developed metrics for the per CWE and per cert rule results. In the paper, late GBM results are provided for that, and the other classifiers perform similarly well. Now this is just holdout data, though. We have not yet tested on natural data, which is natural code bases, which of course are the natural next step. In the paper, we also talk about how we did speculative mapping for tools that don't have a public CWE mapping, and that we didn't have enough effort to be able to map manually. We mapped both forward checker to CWE and backwards CWE to the tool checker taxonomy, and we compared with multiple mapping thresholds both ways. The actual relationship between checker and CWE could be any of the possible Venn diagram options listed here. Only some are shown in the figure. Now, we had unexpected results. We had expected that the classifier would perform slightly better with high threshold matched speculative mappings, but it didn't. And we had expected it to be worse, much worse, for low threshold matches than it was. So speculative mapping was a little disappointing in the performance, but we think that it still could be quite useful. For one thing, for severely underrepresented conditions, it's a possible source of improvement. From our data, at the most inclusive, there are 102 CWEs in training data versus only 82 in the non-speculative training data. We also developed an effort-saving method for mixing automation with manual mapping. By first doing speculative mapping and then manually evaluating those possible matches, the amount of manual effort required to do the mapping is greatly reduced. Here you can see that we measure it as saving a factor of 233 less to do the mappings. We examined feature importance, and the highest feature of importance was alerts for a function called by a local function, which were far more likely to be false positive. We published the open source data used to develop classifiers and make mappings in this work in the RC data set that's published at the wiki that you see there. It's actually a file output from a Mongo database dump. It also includes the Juliet Java test suite data, which was not part of this paper as a case study, but it was created using the auto-labeling system presented in the paper. So that's in addition to the Juliet C++ data, which was in the paper. That's in RC data. The proprietary static analysis tools, alerts, and checker mappings are not in RC data due to license restrictions. And at the URL you see here, there's a blog post with more information about RC data. And we all definitely welcome you not only downloading that data and using it in your research. We would very much welcome any contributions to that data set. So in summary, we developed this novel method to use test suites to generate labeled data. We implemented it in software. In a case study, we generated a large quantity of labeled data for many CWE using the Juliet C++ test suite. And with that, we created 4 types of classifiers and tested on holdout data. We also tested speculative mapping and devised an effort-efficient, part-automated method to map static analysis tools to test suite taxonomies. So next steps, which we have already begun, include working with test suites involving naturally developed and larger code bases, whereas the Juliet test suites tests are 1 to 3 very small files long, and we're starting to test with much larger code bases. We're extending testing to use the classifiers on natural code, and we're attempting to improve classification by using active learning strategically, combining the manually adjudicated meta alerts on natural code with test suite auto-labeled meta alerts. Comments and questions are welcome.